Man has now inched his way to the Earthside edge of space. But before he can set foot on the Moon, or on Mars or Venus, to see and hear and touch, to perceive and come to know for himself the truths now shrouded in these mysteries of the universe, he must build a stepping stone in space. He must soar aloft on the thrust of a rocket engine, as he has in the past. The force of his engine will have spent itself when orbit is reached. So a new array of power will have to be waiting for him, having been similarly borne into orbit by another rocket engine. Now he must assume the same orbit as his new store of energy. He must maneuver both vehicles for capture, then attune his speed to that of his target for joining together. This is rendezvous. This is the stepping stone to deep space and more knowledge of the universe. This mission of work is called Project Gemini. Gemini is a new phase of learning, an intermediate step in which man will gain new experience and knowledge in space. Gemini will reveal to man his capabilities during extended periods of time in space. 1 week, 2 weeks, longer than required for a trip to the Moon and back. His systems of life support, communication, control, propulsion, all must again prove themselves beyond all doubt in this longer test of time. Man will learn to rendezvous in space, to gather his forces for life and propulsion. In Gemini, man will develop a new way to return to Earth, to a pre-selected point on land instead of on water. Dark-shaped inflatable wing called a paraglider will free him from the uncertain drift of a parachute driven by the winds and give him the relative precision of maneuverable flight as he nears the Earth's surface, combined with the capability for a gentle touchdown. Gemini will end only when broad and flexible techniques have been perfected. Techniques that will provide a wide margin for all contingencies of error and permit man to proceed with all possible safety and certainty deeper into space. The time schedule for the successful completion of Gemini is very short. Accordingly, men, equipment, and systems proved in past experience are used as much as possible. Much is taken from the knowledge gained and set down in the open pages of Project Mercury. For instance, the shape and structure of the Mercury spacecraft, so eminently qualified for the rigors of orbital missions, are preserved. The Gemini craft is scaled up to accommodate 2 men and a greater load of fuel, oxygen, and equipment. The men occupy a life-supporting chamber within pressure-tight bulkheads. Equipment is stored in compartments accessible from the outside of the craft. It is arranged in systems, wherein substitutions may be made in modular form rather than by the time-consuming method of replacing various individual components. A seat ejection system provides a means of escape during the periods of pre-launch and initial powered flight. It also serves as an emergency backup to the paraglider landing system. In addition to the Mercury ability to control yaw, roll, and pitch, and to fire retrorockets, Gemini must be maneuverable in space. It must be capable of changing orbital flight path. Therefore, it carries its own propulsion system for increasing its orbital speed, for slowing down, or for moving in all directions. The rendezvous target in Gemini is the Agena rocket vehicle. For launching, the Atlas serves as the primary stage. After the power of Atlas is consumed, its weight is jettisoned. Then the engine of Agena starts and powers the vehicle into orbit. When the desired orbital conditions are obtained, the Agena engine is shut down and preserved for later use. This is a feature of the Agena. Its engine can be started up or shut down on command from the ground or from the Gemini spacecraft once the two vehicles have docked. The spacecraft is boosted into orbit by the two-stage Titan II. And this effort consumes the entire power potential of the Titan, so it too is jettisoned upon completion of its work. Events leading to the ultimate rendezvous of the spacecraft and its Agena target at a given time and point in space present complex problems. It is well that we understand these problems and the approach to their solutions if we are to intelligently follow and understand the progression of work in Project Gemini. One problem would be simplified if the vehicles could be launched from some theoretical point along the Earth's equator. In space, the orbit of the first vehicle would be established in a plane passing through the center of the Earth, the same plane on which the circle of the equator lies. As the Earth turned, our launch point on the equator would continually move under the orbital path of the vehicle in space. Both would move in the same plane. No matter how far the Earth turned between launchings, the second vehicle, launched on the same course, could be inserted easily into the same orbital plane. However, the timing of the launch of the second vehicle is extremely critical in relation to the position of the orbiting target vehicle. This is a problem of phasing. If the launch is timed so that the spacecraft arrives in orbit when the target is at a point halfway further around on the circular path, the two vehicles are 180 degrees out of phase. Although the smaller orbit of the second vehicle permits it to complete each revolution in less time than the target vehicle moving in a larger orbit, the correction rate is relatively slow, and an excessive expenditure of time is required to close the gap and bring the vehicles into phase. For instance, a correction rate of 5 degrees per revolution would require some 36 orbits to correct a 180-degree phase differential. It is extremely difficult to launch a vehicle at an exact time. Weather, equipment, and systems checkouts cause unpredictable delays. Excluding all other factors for the moment, the phasing problem is minimized by launching the second vehicle during a given period of time that will place the craft in orbit within some 60 degrees or less of its target. This differential in phase may be overcome in a more reasonable length of time. Now we have the additional task of making the two orbits coincide. This is done by speeding up the craft on the small orbit or slowing down the target vehicle, producing in either case an elliptical orbit which becomes tangent to the remaining circular orbit. This is done at precisely the right time so that both vehicles arrive at the tangent point almost simultaneously. Then another slight adjustment in speed is made so that the orbits coincide and the vehicles can dock together. We have accomplished the placing of two vehicles in the same orbital plane with relative ease because our launch site has been a theoretical one on the equator. The United States and the Cape Canaveral launch site lie far north of the equator. The circular path Cape Canaveral follows as the Earth turns does not lie on the same plane as the equator. Nonetheless, a vehicle launched at Cape Canaveral will always assume an orbital plane that does pass through the center of the Earth, similar to the plane of the equator, but at a different angle. Consequently, the plane of the orbit is quite different from the plane of the circle through which Cape Canaveral moves. Although the orbital path of the vehicle remains constant in space, its relationship to Cape Canaveral constantly changes as the Earth rotates. The launching site moves out from under the path of the orbit and passes beneath it at just 2 points in a 24-hour rotation of the Earth. It is only at one point, however, that Cape Canaveral's position in relation to the orbit is the same as it was at the time of the launch. And it is in this period, lasting just an instant, that a second vehicle may be launched ideally into the same plane of orbit as its target vehicle. This fleeting period of time is called the window of launch. If Cape Canaveral is allowed to move away from this optimum launch position before launching the second vehicle, the orbital angle of the second craft is different than that of the target. The further Cape Canaveral moves, the greater the angle differential of the orbital planes. The spacecraft can correct this difference in angle by changing its course in space, but to do so requires a considerable amount of fuel in relation to its fuel capacity. Fuel provisions in the Gemini spacecraft, combined with proper launch techniques, extends the time in the launch window from just an instant to an hour and a half. In Gemini, orbital flights are planned in relation to the ground tracking network that extends around the world. To provide maximum survival possibilities in emergencies, when the spacecraft might be forced to land at some point other than that provided for in an ideal schedule, the network extends along a ground track that lies predominantly in the temperate zones. As the orbital flight continues on a constant course in space, the Earth's rotation gradually moves the tracking network out from under the direct path of the spacecraft. At various points in ensuing orbits, however, the flight path will move over certain segments of the network and come within range of certain stations. This allows intermittent communication with the vehicle in periods of short duration. The inertial orbital period is some 90 minutes, Thus, a quick computation tells us that in 24 hours, the spacecraft will accomplish some 16 inertial orbits, while the Earth completes one revolution. The 16th Earth orbit of the spacecraft follows approximately the same track over the Earth as the first orbit. This provision allows the craft to land at the end of the 16th, 17th, or 18th orbit in pre-planned areas adequately manned by recovery forces. Although the spacecraft can manage its own re-entry and landing with limited intermittent communication and control from the ground, the best interests of safety and success dictate that a Gemini mission be limited to 3 orbits, or extended to 16, 17, or 18 orbits, or to 32, 33, or 34 orbits, and so on. The vulnerability of a launching countdown to delays may require a still longer window of launch. Therefore, the multiple restart capability and the performance potential of the Agena provide additional flexibility which allows the window of launch to be extended to as long as some 4½ hours. Agena is inserted into a circular orbit. The Gemini spacecraft is launched at an optimum time, say 24 hours later, for insertion into the same orbital plane. Its orbit is elliptical. Any small angular difference in the planes of the 2 orbits is corrected by applying a propulsion force in the desired direction perpendicular to the motion of the spacecraft. With its motion thus bent, so to speak, the orbital plane of the Gemini craft is corrected and made to coincide with the orbital plane of the Agena. A similar maneuver by Agena would achieve coplanar orbits. The Gemini spacecraft, in the apogee of its orbit, accelerates with very little expenditure of fuel to a velocity sufficient to acquire the circular orbit of Agena. If it is desired to speed up the phase correction rate, the Agena is reignited and inserted into an elliptical orbit of sufficient magnitude to achieve any correction rate desired. Then the Agena is commanded to slow down. Its reduced velocity diminishes the size of its orbit until its original circular path is re-established. The terminal stage of the mission begins as the 2 vehicles assume positions in space within range of the Gemini onboard radar system. This system provides constant information on range and range change rate. At a glance, the astronaut can determine his distance from the target, the rate at which he is closing that distance, and whether he is proceeding along a satisfactory course for interception of his target. An alternate system that can be used separately or in connection with manual control and radar guidance is provided by an onboard computer armed with a multitude of prepared equations. The radar information speeds through the computer, and the constant flow of computed results is transposed instantly into electromechanical factors that automatically apply the spacecraft's propulsion force at the exact time, in the required vector, and for the necessary duration to maintain a continually proper course for interception of the target with minimal expenditure of fuel. When the 2 vehicles are within some 20 miles of each other, they enter what is called the volume of capture. The radar system with manual control or with automatic control may be used to guide the spacecraft on into its target. Or the astronaut may elect to conduct this maneuver under direct visualization. If so, he observes his target against a star background. He can see the relative motion between the 2 vehicles. He fires short bursts from the Gemini propulsion system, producing a constant line of approach that will intersect the path of his target. Now the 2 vehicles, rushing through space at some 18,000 miles an hour, share a gentle difference in speed of 1, perhaps 2 miles per hour. The flexibility of man control is ideal for threading the nose of the Gemini through the docking collar of Agena. Sometime during a Gemini mission, an astronaut may unlatch his pressure-tight hatch, open it, and look out of his cockpit into space. He may even climb out and see what it's like, protected all the while by the life-supporting atmosphere within his pressurized spacesuit. His initial objective accomplished, the astronaut prepares for his return to Earth. When man has learned to live and work in space for extended periods of time, when the best possible methods of rendezvous have been determined and demonstrated, and when point landings can be made with consistent success, the first phase of Project Gemini will have been accomplished.